3-phase 3-wire static voltage optimizer designed and developed by Medi. 66 kVA to 660 kVA, 100 ampere to 1000 ampere in each phase. This is a 100 kVA system with each phase 150 ampere output current for the demonstration.
This is Medi's 3-phase 3-wire vector control static voltage optimizer or static voltage stabilizer. Voltage optimizer or stabilizer is for energy saving or regulating the voltage. Our system is based on direct AC to AC PWM using IGBTs. The main advantage of this system is it works without neutral. Only 3-phase 3-wire input is required. The 3-phase 3-wire output has a potential with the existing neutral, so single-phase load can be connected from any of the phase output to an external neutral.
This is the functional block diagram of the system. Since only the difference power is processed, much less current will flow through the IGBTs. For example, for a 100 ampere 52 volt correction in each phase, only 9.2 ampere will flow through the IGBTs. A 66 kVA system needs only 12 kVA 3-phase buck-boost transformer.
This is the control PCB. This is the DSP. This is the SMPS section. These are SMD inductors for the SMPS, and this is the SMPS ICs. These are optocoupler triacs for driving the contactors. These are EMI filters. This is the RS485 section. This is the isolated RS485 communication port. This is the SMD transformer for isolated power supply for RS485. The LCD will show parameters like AC input, AC output, load, etc. This is the AC input and this is the AC output. These are for IGBT driving signals. A second connector is used for interleaved switching above 0.5 megawatt operation. The PWM drive from the DSP is connected to 3-phase self-powered IGBT driver PCB. In this 3-phase self-powered IGBT driver, the isolated power supplies plus 15 volt and minus 8 volt to all the IGBTs are generated internally. There is no need to provide an external isolated power supply. These are the SMD transformers used for isolated power supply. These are the gate drives connected to the gate and emitter of each IGBT module. Each gate drive has a peak current of 15 ampere sink-in source. These wires are connected to the collector of each IGBT module for desaturation sensing. During desaturation, a soft turn-off of IGBTs is provided. This will avoid high voltage spike across the collector and emitter of the IGBTs during turn-off. This is the 3-wire input. The input range in delta VO is 381 volt to 433 volt. You can see the 3 wires R, Y, B. The input is going to the IGBT through a spike protection circuit. These MOVs will suppress any high voltage spike and can absorb maximum current of 40,000 ampere for about 8 to 20 microseconds. These are the IGBT modules, and here the PWM output will come. This PWM output is fed to this low pass filter, which will integrate the PWM and produce the 3-phase sine wave output. The amplitude of this sine wave will vary according to the PWM duty cycle. This will be shown later with an oscilloscope. This 3-phase sine wave is fed to the primary of the buck-boost transformer. This is the buck-boost transformer. Since the primary voltage is varying, there will be a corresponding voltage variation in the secondary as well. This secondary is connected in series with the AC input. So this voltage can be added or subtracted with the incoming AC voltage. This is the AC input. This is the output. The output is connected through a contactor. This is a nickel zinc ferrite core for EMI filtering used both at input and output. These are X1 capacitors used for EMI filtering. These CTs are for sensing the output current. This is the bypass contactor. In case of overload or high temperature or any hazardous condition, the unit will bypass without interrupting the output. A 3-phase motor is connected to the VO. For loading the 3-phase motor, a generator is coupled to the 3-phase motor. Output of the generator is connected to the bulb load with switch, so we can vary the load.
These 3 meters are connected to the output. These 3 meters are connected to the input. Channel 1 yellow of the oscilloscope is connected to the output R2I. Channel 2 blue of the oscilloscope is connected to input R2I. Now we are applying the input voltage to the system. You can see the input in the meters as well as in the oscilloscope. Let us switch on the system. See the output in the meters and in the oscilloscope. Now we are varying the input voltage. You can see the variation in the meters and in the oscilloscope. You can see the output is steady in the meter and oscilloscope. Now the channel 1 of the oscilloscope is connected across PWM R2I. Let us switch on the system. You can see the PWM R2I in the oscilloscope. Let us expand the PWM. Now we are varying the input voltage. You can see the PWM is varying for correcting the output voltage. The block diagram shows a 3-phase delta load connected to the system. It also shows the connection of a combination of 3-phase delta load and single-phase load connected to an external neutral.
See, here I took a separate neutral. The neutral I brought here, so the neutral is coming here. Then you can connect single-phase load like neutral to any of the phase. See, neutral to this phase or neutral to this phase. I will show you the voltage of the neutral to that phase. You can see the voltage to neutral. See the voltage, you see. This is 222, and phase to phase voltage you can see. The phase is 385. So you can connect 3-phase load from here. Then single phase load you can take a separate neutral and you can connect.
Now we connected the oscilloscope to the output. We are varying the input voltage. You can see the output voltage is steady. Let us switch on the bypass contactor. As you can see, there is no interruption in the output waveform. Now the system is in bypass mode. When we vary the input voltage, you can see there is a corresponding change in the output voltage. This load is about 20,000 watt. These are delta loads. And this load is a single phase load for which we have taken a separate neutral.
The channel 1 of the oscilloscope is connected to the output R2I, and channel 2 of the oscilloscope is connected to input R2I.
Now we have switched on the load. You can see the load.
Now you can see the load regulation in the oscilloscope. Now I switch on the load. you can see the CRO. Yellow is the output voltage, blue is the input voltage. Now I switch off the load, again switch on, again switch off. You can see the input voltage dip, but output is steady and there is no harmonic distortion. See there is no harmonic distortion. You can see now. Switch on the load also, switch off. You can see that. See in that there is no harmonic distortion. But the voltage dip, you can see the voltage dip in the input, but output is steady. The fast correcting, it is correcting very fast. Now you can see the load regulation. Now I switch on the load, now switch off, then immediately it is correcting. Now suddenly switch off all the load, suddenly switch on. That time the PWM regulating. See the surge load, because of the surge load, it is correcting again, slowly came back because of the halogen lamps and motor. See the input voltage, you can see, zoom the meter here, input. That switch off time, the voltage increase. Switch on time, that is reduced. Here also you can see switch off time, the voltage increased, and switch on time reduced. Now about 20 kilowatt mixed load is connected. See the output current. It is 22.23 ampere. See the input current same time. It is 21.2. So this is how much is it. Now it is operating in VO mode, voltage optimizer mode. The system will go every 1 hour or half an hour. It will go to bypass mode and see how much is the actual power consumption, and it will go back to voltage optimizer mode and calculate how much is the savings. Now you can see the input current and the PWM. Now this is operating in VO mode. So now I will change to bypass mode. So smoothly it will go to bypass mode. You can see the PWM reducing and the input current is increasing. Now this went to bypass mode. Now again I switch on the VO mode. See the input current reduction.
Now already the load is switched on. We are going to short circuit the output along with the load. Now let us short circuit again. We are going to short circuit other two phases along with the load. The unit has tripped safely. Now you are seeing the PCB through a thermal imaging camera. Let us switch on the system. You can see all the components on the PCB are working within the temperature limit.
You can see the temperature of DSP is 28 degrees Celsius. Let us switch on the unit. You can see the rise in temperature of the DSP, 38 degrees Celsius. The inductors and SMD IC for the SMPS section, the temperature is 32 degrees Celsius.
SMPS section, this is the SMPS IC, this is the SMPS IC, this is the inductor. See, this is the inductor, this is the next inductor. So that IC, you can see SMPS IC, the temperature is 35. This is another IC. See, all are in the limit. See, you can see the temperature of the RS485 regulator IC. It is only 36. Then here you can see this is the optocouplers for RS485 that also remain cool, just warm. Now you can see the temperature of the IGBT drive PCB in the thermal camera. That I will show you that IC. Let us focus this IC. See that IC temperature only 30. See that all the IC remain in the same temperature. See, this is the transformer. That's only 33 degree. I will expand the PWM. See that because of active clamping, you can see that PWM is very smooth. See the PWM, there is no spike at all. The rising and falling edge you can see. No spike. I will increase and decrease the PWM. See that absolutely very clean PWM because there is no spike here because of active clamping. Here I connected the CRO. Here channel 1 yellow I connected here. This is R minus Y. See, this is R minus Y. Then channel 2, this is Y minus B. Then this is B minus R. So in the CRO you can see this is R minus Y, Y minus B, B minus R. Now you can see the PWM. See, I will increase this. See, now you can see the PWM. So I am varying the PWM. See, now the PWM percent is maximum. Now the PWM percent is minimum. So, see, I will show you. See, this is the three-phase direct three-phase AC to AC PWM. See, this is Y. See, now you can see that all are in the directly delta in three-phase delta PWM. We are doing direct delta without any neutral, only this PWM is doing. Because IGBTs are connected in anti-series, then directly AC to AC PWM is possible. Now you are seeing the PWM output of this IGBT module. I taken the PWM 0 connected. This is R minus Y. R minus Y I am showing. That is here you can see. Now you see the PWM. I expanded the wave. So now the PWM width is medium. Then now the PWM width came less. Now very low width. Now again the PWM width increase because I am varying the input voltage by thermostat. That time it is correction, then fast correction. Now that if I increase the load also for adjusting, the PWM will vary slightly for adjusting the output voltage. So this PWM, there is an AC to AC switching PWM. See, negative half and positive half. You can see the positive and negative half. This is going to that this filter. This is that high frequency filtering amorphous core, and this is X1 capacitor. Then here sine wave output will come. Now the CR had changed to that point. So I told here you saw the PWM. So this is R minus Y. Here also R minus Y. This is after filtering. This after filtering I connected the oscilloscope. See, R minus Y. So that waveform you are seeing in the scope. See, now the PWM integrated in the sine. So I am varying the input voltage. That time I could for the correction, output correction voltage. See, now PWM reducing. That time output voltage. Now PWM increase, output voltage increased. Now PWM reduce, output voltage reduce. See, now that temperature of this core is here. It is slightly warm. Now 30 degree. But this is for 50 Hz filtering only. This is almost same. Both you can see that. Now you see that both the core at a time. See, this is that EMI filter. Other is that other core. See the temperature, that only that core only, because that is the high frequency filter. So that is amorphous core, that is slightly warm, just slightly warm, but this is remain cool, 28. That is 30 degree. After 1 hour, 31. That's it. See the core heat. 31, but see this core, this is still cool.
There are two modes of operations in this system: voltage stabilizer and voltage optimizer. In voltage stabilizer mode, the system will give plus or minus 1% regulated output for a varying input voltage. In voltage optimizer mode, the system will always track at what voltage the minimum energy is consumed. Simply reducing the voltage will not save energy in all cases. For a motor load, if you reduce the voltage, the power consumption will increase, and increasing the voltage will also make the power consumption increase. The minimum power consumption is at a certain voltage.
In this graph, you can see the minimum power consumption point of a motor load.
The DSA will track this point by varying the PWM and maintain the PWM for minimum power consumption. This minimum and maximum tracking range can be set in the unit. The voltage will not go beyond this limit.